2.2. Okay, 2.2 is on determining volumes by slicing. Okay, determining volumes by slicing. Okay, so we're going to think of a volume and we're going to think of it as infinitely many little slices. Okay, and those slices, they're just changing in size. Okay? So volume by slicing method. And then we're going to sum up all those individual infinite slices to make one solid piece. Okay? So number one, examine the solid and determine the shape of the cross section of the solid. Okay, what would the cross section be? If you slice this down through the, vertical, okay, or horizontal, what's the cross section look like? Is it a triangle? Is it a square? Is it a circle? What does the cross section look like?
A rectangle?
Well, I haven't put up the picture yet. Okay. So it depends on what we're finding the volume of, right? If we find the volume of a cylinder, what are the cross sections? What would be the cross sections of a cylinder?
Circle?
Circular?
It would be a circle, yeah, exactly. If I took a pyramid, what would be the cross section of a pyramid?
Triangle?
It would either be a triangle or it could be a square.
Square.
Like the pyramids in Giza, right? Right? They're square base, right? So if you took cross sections, wouldn't you just get smaller and smaller squares? Right? Does that make sense?
Right.
Yeah. So it all depends on the shape of the volume that we're looking at. Right? So examine the solid and determine the shape of the cross section, okay, of the solid. Number two, determine the formula for the area of the cross section. Okay. Determine the formula for the area of the cross section. So we should know what's the area of a square, what's the area of a rectangle, what's the area of a triangle, what's the area of a circle. Okay. Those are just basic geometric formulas. Okay, number three, integrate the area formula over the appropriate interval to get the volume. Integrate the area formula over the appropriate interval to get the volume. Okay, number one, derive the formula for the volume of a pyramid with a square base using integration. let's find the volume of a pyramid with a square base. Okay. Using integration. Okay. So let's draw a pyramid, but let's orient the pyramid with respect to the x-axis. So this is going to be kind of like a pyramid tipped on its side. Okay, so again, the pictures are going to be the hardest part of today's lesson. Okay, so we want a pyramid of some height. So I'm going to draw some straight lines here. I'm going to attempt to. Okay, let's draw that one. Okay. I think that's good. Hopefully that's good. Okay. And I'm going to connect these, okay, with another line. Okay, okay. Now we're going to give our pyramid some depth. Okay, so let's connect. Let's draw some more lines here. So I'm going to draw another line. Okay, like so. And then I'm going to go straight down. And then I'm going to go straight down again. And then I'm going to go up. Right? I'm going to highlight this one a little bit as well. Okay. So far, so good. Okay, I'm also going to draw a line right here. Okay, and then I'm going to connect some lines. 3 of them to be exact. I'm going to connect, oops, not that one. I'm going to connect this to here. Okay, and I'm going to connect this to here. Well, that doesn't think it's a line, so let's try that again. Okay, and one last one. We're going to connect to this. Oof. Okay. So now I'm going to draw this guy and that guy. Okay, that's there. This is going to go down to here. This is going to go up there. Okay. So far, so good. Okay, I'm not drawing the 4th line because this is going to make it really messy, and just think of this like as just, you know, the 4th line is there, the 4th corner is there, but if I draw that line, I just feel like it's going to make it totally messy, and you should get the idea from the picture that I've drawn what's going on. Okay. Okay. So if this has side S, which is the side length of the base of the pyramid, okay, then we're going to call this guy here A. Okay, A is going to represent the length of one of my slices. Okay, so I'm gonna slice this thing up and create squares. Okay, and so this slice here that's in the middle, that slice there, has length A, okay, side length A. And it's out X units. Okay, so from here to here is X units. Okay. So far so good. Okay, I'm gonna draw the triangle in the middle. I'm just gonna talk about the triangle that's in the middle here. Okay, so what's the triangle that's in the middle? Okay, well, okay, it's just this triangle. Okay, it's in the middle. Okay, so, and we're gonna use similar triangles and a couple other things to help us figure out, you know, the relationship between S and A. Okay, we know that the height of the pyramid is known. And that's H. H is the height of the pyramid. So if we look at this guy here, okay, we know that, maybe I'll draw it in a different color. We know that this here is A. This here is X. Okay. And so we know X to A, or maybe we'll say A to X. A to X is the same as what? Same as what?
Is it S over H?
It is. It is S over H. Okay, because this was S and this whole thing was H. Make sense? Okay. Okay, so now what do we know? Well, we can solve for A. So let's solve for A. Let's multiply both sides by X, and we're going to get a function in terms of X. So every A that I could create inside any slice that takes on the value of A is just a formula, S over H times X. Oh, okay, well, that's convenient. Okay. So this is where S is the side length of the base. Of the pyramid. Okay, cross sections are squares. Those squares just happen to increase in area. Okay. And so what can we say? What's the area, okay, based on X? What's the area based on X? If I go out a certain X, what's the area of that cross section going to be? Well, what's the area of a square? The area of a square is just the side length squared. That's the area of a square, right? The area of a square is a side length squared. Okay, and we're just saying, hey, maybe I should not use S. It's the side length times itself. Okay. In this case, A is our side length. But we can rewrite that in terms of X. Okay, so forever how long I'm out X units, I can find the area of that square. by using, by knowing that what S is, what H is, and how far out X is. I'm just gonna go here and I'm gonna take the base area, or the area of that area of that cross section. Okay, and I'm going to plug in S over H times X, and I'm gonna square that. This will equal S squared over H squared times X squared. So that's the area of the cross section. Okay, that's good. So to find the area of the pyramid, we're just gonna add up all of the infinite cross sections that we can have. Okay, so let's use an integral to do that. We're gonna integrate from X equals 0 to X equals what? How far out will X go? X will go from 0
H.
to H. Thank you, Elijah. Yeah, it will go out to H. And then we're going to say, well, this is just S squared over H squared times X squared dx. Right? So now, well, S squared and H squared, those guys are just constants. Okay, so I can actually pull those out, or I could leave them in. It doesn't really matter. But the only variable that is going to get integrated here is X. And so this becomes S squared over H squared times X cubed over 3 evaluated from 0 to H. Okay, good. Okay, so let's plug that in. We got S squared over H squared times H cubed over 3 minus S squared over H squared times 0 cubed over 3. So this is going to go away because it's 0. Okay, and the H's are going to cancel. I've got 3 H's on top, 2 H's on bottom. That just leaves me with 1 H. I'm going to rewrite this a little bit using algebra. This is 1/3 S squared times H. Okay, and that's the area of the pyramid. That's the formula for the area of a pyramid with a base of a square with side S. Okay, so area with base I should say square base, area of, well, let's say area of a pyramid with base of, with square base with side length S. Okay, which kind of makes sense to me because when I was taking geometry, I remember the geometry teacher would say the area of a pyramid is 1/3 base area times the height. And the S squared there, that's just the base area. H is the height. So it does kind of line up with what I learned in geometry. Okay. Okay, any question on number 1? Okay. Let's talk about creating discs, creating circles. Okay, as our cross sections. These are going to be called solids of revolution. We're going to take a function and then we're going to revolve it 360 degrees to create a solid of revolution. And whenever we do that, the cross sections are going to be circles. Okay? So creating discs. Okay, the area of a circle is pi r squared. Okay. If we revolve f of x about the x-axis, then letting f of x be the length of our radii, we can obtain the volume of the solid by integrating a to b, maybe I'll put this on the next line, a to b of pi times f of x squared. Maybe I'll put that in brackets. Dx. Okay, where x goes from a to b. Okay, so we just let our radius vary with respect to f of x. Okay, if we rotate about the x-axis, then the height of our function will just be our radii, and that will be the radius of the cross section of the solid that we're creating when we revolve that around that function around the x-axis. Let's do an example and see how this works. Number 2. Find the volume of the solid obtained by rotating y equals the square root of x between x equals 0 and x equals 1 about the x-axis. Okay. So let's look at the square root of x here. Okay, make this 1, make this 1, 0. So the square root of x looks like this. It's kind of like a parabola tipped on its side. Goes like this. It's a nice curve. Okay, that's the square root of x. Okay, if I were to the bottom here, remember I'm rotating this, right? Rotating this 360 degrees. So what's that going to look like? It's going to look like maybe a bowl or a cup. Okay, so this is at 1. Okay, and so this is the solid that's created. Now, my individual cross sections are going to be circles. Circles of radius f of x. See, f of x, if I'm out x units, okay, then f of x is going to be the height of my function. And that's going to create the measurement for the radius. Hmm? Does it make sense? Like, as I revolve this, the height of that function creates that radius for that one slice, for that one cross section, and then we're gonna sum up all the infinite slices using integration. Hmm? Okay, so the volume of this thing is equal to the integral from 0 to 1 of pi times the square root of x squared dx. Okay, that's good. Okay, why? Because the square root of x is r, it's the radius. Okay, this is, okay, that's what r is. So then we sum up all of our slices to get the total volume. Okay, this is going to give us an area of one slice, and then we're going to add up all of those slices to get the volume. Okay, so the volume is equal to, I'm going to pull the pi outside, because if I'm summing up things, if you multiply a sum, each term of the sum by the same thing, you can just multiply the whole thing. It's it's just the distributive property in reverse. We just factor it out. We factor out the pi. And this becomes a square root of x squared. Well, that's just x. Okay, especially on the interval 0 to 1. Okay, so we've got x and then dx. So this should be pretty simple. Okay, this should be pretty simple to integrate. So this becomes pi 0 to 1 of x dx. So that's just going to become x squared over 2 from 0 to 1. This becomes pi times 1 squared over 2 plus 0 squared over 2 is equal to pi times 1/2 plus 0, that goes away, this goes to 0, and we just get pi times 1/2, which is pi over 2, which is our answer. Okay, now the question is, well, what happens if we want to revolve around the y-axis? Well, we have to put everything in terms of y then. So if I say that to revolve about the y-axis, we solve the function for x which gives us f of y as the radii and the volume of the solid is found by integrating the integral from c to d of pi times f of y squared dy, where y goes from c to d. Right? So we just put everything in terms of y. We take the same function, but we turn everything in terms of y. Okay, so let's try the same function, but let's now rotate it with respect to y-axis. Okay, so what would that look like? If I take the same function, my y equals x function, my y equals square root of x function. Okay, let y equal the square root of x. And we want to rotate this thing about the y-axis this time. So we're going to get something kind of looks like that. Rotate. So this is kind of looks like a funnel. Whereas the other one looked like a bowl, this one kind of looks like a funnel. Okay. Okay, our cross sections are still going to be circles. Okay, but the circle radius is now going to be f of y. The circle radius height, or length in this case, is going to be f of y. It's going to be a function with respect to y. Okay. Okay, so let's look at number 3 here. Find the volume of the solid obtained by rotating y equals radical x about the y-axis from 0 to 1. Okay. Okay, so let's take y equals radical x, let's solve it for x. So we get a function in terms of x. I mean, in terms of y. So let's square both sides. And we get y squared is equal to x. Or x is equal to y squared. Or f of y is equal to y squared. Now I have to ask myself, where does y go from? If x goes from 0 to 1, okay, then what does y go from? Well, if I plug 0 into the original formula, I get y equals 0. If I plug 1 into the original formula, I get x equals 1 or y equals 1. So it has the same limits of integration because I'm going from point 0, 0 to point 1, 1. Okay, so in this case, it just happens to be the same. In every other case, it will not be the same. So you're going to make sure, you've got to make sure you're not using the x limits, you're using the y limits. If you're integrating with respect to the y, rotating with respect to the y-axis, make sure that your limits are with respect to the y. That's this guy and this guy. Right? Okay, so let's put all the pieces together and integrate. We're going to take the integral from 0 to 1 of pi of f of y squared. Well, f of y is y squared, so this is going to be y squared squared dy, which is 0 to 1 of pi. I can bring the pi out. This is y to the 4th dy, which is then pi times y to the 5th over 5, evaluated from 0 to 1. plugging in 1, I should end up with 1/5. And I do. Becomes pi times 1/5, which is pi over 5. Which was smaller than the pi over 2. Does that make sense? That this volume that looks like a funnel would be smaller than the volume that looks kind of like a bowl? Yeah, it's less volume. Okay, because here it bows out and creates more volume. Okay, here it's bowing out, but it's creating less volume between the two functions. Okay,
Professors, sorry to interrupt.
yeah,
So at the top, you added, or the one before this, you added at the end of the integral, but at this one you subtracted at the end of this one. Why do you add?
oh, I'm sorry, this is a subtraction.
Oh, okay. Sorry about that.
Yeah, thank you for catching that. My bad. Okay. Yeah. Okay, any other questions?
Can you also clarify a little bit about the limits? Because you said we're just inserting 0 and 1 into the original equation, which is what is it? Y is equal to square root of x.
Right.
So wouldn't it be square root of wait, is
So if I take y equals the square root of 0, I get 0.
oh, I'm sorry. Never mind.
Right?
I got it.
Cool. Awesome. Okay. So let's see what happens when we have two functions. Okay, two functions to deal with. So this is called creating washers. Okay, and if you know what a washer looks like, it's a circle inside of a circle. Okay, and we only care about this piece. Okay, it's like taking the cross section of a donut. Okay, we only care about the area between the two circles. And so creating washers. I know if you're haven't done anything real mechanical, you may not know what a washer is, but it goes on the end of a bolt to help you fasten the bolt to something. Okay. So creating washers. Okay, number 4. Find the volume of the solid obtained by rotating the region enclosed by y equals x and y equals x squared about the x-axis. And the volume of the solid obtained by rotating the region enclosed by y equals x and y equals x squared about the x-axis. Okay. So let's maybe draw a picture of this. Okay. Y equals x, that's just a line at 45 degrees. Okay, that's just that line. Okay, this line y equals x. Okay, y equals x squared is a parabola. Let me draw the line. Let me draw the line a little bit. I'm gonna draw an actual straight line. Or not. Well, you know what? I could just use a ruler. So let's just use a ruler. I'm not gonna be able to freehand this really well. Oh, there's my 45. There we go. Much better. Got one. We got one. There. This. Let's get rid of my ruler. Okay. Better. Okay, so now we're gonna draw a parabola. It goes like this. Okay, so now where are they intersecting? Well, looks like they're intersecting at 0 and 1. Right? We could prove this by saying, well, where is x equal to x squared? Well, we could toss x to the other side. We get x squared minus x is equal to 0. Okay. And so factor out an x, and we get x equals 0 or x equals 1. We know that the endpoints are 0, 0 and 1, 1. That's at 1, 1. That's at 0, 0. Okay. Which function is on top? Which function is on top? The function that's on top is y equals x, right? And the function that's on bottom is y equals x squared. That'll be important. Okay, so what are we going to calculate when we rotate this thing about the x-axis? What are we going to calculate? Well, we're going to calculate, okay, the washer here. Let me draw another line, an auxiliary line here. Okay. Draw that auxiliary line. And this is going to be a circle. That guy. And then what about we're going to end up having a washer here. We're going to end up having an outside circle. And we're going to end up having an inside circle. Which will mean that we are getting these washers. Okay, so how am I going to find the area of the washer? How am I going to find the area of the washer? How would I find the area of the outside circle minus the inside circle, right? So outside circle minus the inside circle. He's gonna create this washer here. Right? Mhm. Okay. So we want to know, well, what's the outside radius? What's the outside radius? Or we'll say the outside. Yeah, what's the outside radius? Is the outside. We'll say what's the area, right? What's the area? The area is going to be pi times the outside radius squared minus pi times the inside radius squared. Okay, so to find the area of the outside circle minus the area of the inside circle, okay, we want to get the outside volume when we rotate minus the inside volume. Okay, outside volume minus the inside volume. Okay. So we can rewrite this as the area from A to B of pi. We're going to call f of x the outside. Okay, so f of x will be the outside radius minus, that there's a dx there. There's a squared, so dx minus from A to B times pi times the inside, so g of x squared. Right? Dx. Well, since they're going from A to B, and they're both being integrated with respect to x, and they both have pi, I can combine this into one integral. Okay, that integral, A to B, well, let's factor out the pi first. This is f of x squared dx minus pi times A to B of g of x squared dx. Now I can factor out the pi, combine this into one integration. Okay, this can be A to B pi times A to B, okay, of f of x squared okay, minus g of x squared. Okay, pulling the pi out in front, I just factor the pi out. Okay, and then I can put the f of x squared minus g of x squared dx in one integral, because that's a law of summation and a law of integrals. Okay, if I'm subtracting two terms, I can break them up into two integrals. Okay, and here I just use that in reverse, that idea in reverse, and if I'm subtracting two integrals, I can combine them as long as the limits are the same. Okay, okay, and this is called the washer method. Okay, it's when I have a disk inside of a disk. Okay, I still call the washer method. I'm going back, since y equals x is above y equals x squared in our picture, right? In our picture, y equals x is above y equals x squared. Okay. Then f of x is equal to x, which is the outer radius. Okay, and g of x is equal to x squared, which is our inner radius. Outer radius, inner radius. Okay. Okay, so we're going to use our formula here that we derive, and we say, okay, that's pi from, okay, our limits went from 0 to 1 with respect to x of x squared minus x squared squared dx. Okay. It's going to become pi, okay, integral from 0 to 1 of x squared minus x to the 4th dx. Okay, good, good, good. Okay, now let's integrate. This is x cubed over 3 minus x to the 5th over 5 from 0 to 1. Okay, and that's all going to be multiplied by pi at the very end. Right? So this is going to become pi times 1 cubed over 3 minus 1 to the 5th over 5 minus 0 cubed over 3 minus 0 to the 5th over 5. Well, again, this thing goes to 0. This thing over here is 1 cubed over 3, which is 1/3. This is 1 cubed over 5, which is 1/5 times pi. This is 5/15 minus 3/15, which gives me 2/15. So this is 2 pi over 15. Okay. Okay, any question on number, what was that, number 4? Any question on number 4? Okay. Let's talk about what happens when we don't rotate about the x or y axis, but we rotate about a different line. Okay, we rotate about some auxiliary line. Rotating about auxiliary lines. Okay, do an example. Number 5, find the volume of the solid obtained by rotating y equals x squared about the line y equals 1. Right? Okay, 4. Okay, 0 to 1. Okay, so now we're going to rotate not about the x-axis, but we're going to rotate about the line y equals 1 and see what happens. Okay, so let's draw a picture. And I'm gonna put 1 up here. I'm gonna put 1 here. This is 1, 1. Okay, I'm gonna get my parabola, which is gonna look like this. Okay. And now I'm gonna rotate that curve. Actually, a little bit bowed out. Bow it out. There we go. Okay, and then I'm gonna take this curve from 0, 0 to 1, 1, and I'm gonna rotate it around the auxiliary line y equals 1. Okay, I'm not rotating about the x-axis, I'm rotating now about this auxiliary line. So I'm gonna so this becomes the ball that I'm looking at. Okay. I'm gonna get an inside slice. So now I've got to figure out, okay, what's my R? What's my radius? How do I figure out my radius? That little green line right here. How would I find the length of that radius? You know, this is y equals x squared. This is the line y equals 1. That's y equals 1 right there. And then the bottom is y equals x squared. So how would I find that distance? Any ideas?
1 minus x squared.
What is it?
1 minus x squared.
Yeah, 1 minus x squared would give me that top. 1 is the whole thing. Y equals x squared. Y equals x squared is just this height, right? So if I want the whole thing, which is 1 minus this height here, we would get that, right? That should be R. I'll put that in green. Okay. So now this is going to create a disk, right? This is going to create a disk. Okay, with radius equal to 1 minus x squared. Here it is. I'm not going to. Okay, so this is a disk, not a washer. So disk method, not washer. We're going to say, okay, well, this is going to go from A to B of pi times f of x squared, okay, dx, okay, this is really R, okay? And so what is f of x? F of x is this whole thing. It's the radius. So the f of x is the length of the radius. Okay. So we're still going from 0 to 1. Okay, so let's plug in what we know. 0 to 1 of pi, I'm going to bring the pi outside. F of x is 1 minus x squared squared dx. Okay, so we're going to go pi 0 to 1. We're going to multiply this out. This becomes 1 minus 2x squared plus x to the 4th dx. We're just multiplying that by itself, FOIL it out. Okay. So now we want to integrate x minus 2x cubed over 3 plus x to the 5th over 5 from 0 to 1, pi out in front. Okay. I would hope by now that if you see that I plug in 0, everything's going to go to 0. I mean, I'll still write it out for y'all, but eventually I'm going to get tired of kind of writing out what goes to 0. Now, keep in mind that certain things in trigonometry do not go to 0. Only polynomials go to 0. Okay, you can't take the natural log of 0, and the cosine of 0 is not 0, it's 1. So just be careful plugging in 0 and thinking that everything goes to 0 and it's gone. It only works with polynomials. This is 1 minus 2/3 times 1 cubed plus 1/5 times 1 to the 5th minus, this is 0 minus 2/3 0 cubed plus 1/5 is 0 to the 5th. Close bracket. This all goes to 0. And so we're left with pi times 1 minus 2/3 plus 1/5. This is going to be 1/3 plus 1/5. Times pi. This is going to be 5/3 or 5/15, sorry. 5/15 plus 3/15 is 8/15. So this is 8 pi over 15. Okay, number 6. Find the volume obtained by rotating the region enclosed by y equals x and y equals x squared about the line x equals -1. Okay. So we saw from the previous example that the area enclosed by these two things looks like this. Okay. And this time, and this goes from 0, 0 to 0, 1, or so 1, 1. Okay. You saw that from the previous example, but we want to now rotate it around this auxiliary line, x equals -1. Okay. So instead of rotating about the y-axis, okay, we're rotating about this auxiliary line. Now we are rotating in the direction of the y-axis. So this is a y-oriented rotation. Because it's a y-oriented rotation, I need to solve everything for x. Okay. So for y equals x, that implies x equals y. For y equals x squared, that implies that x equals the square root of y. Okay, and we take the positive, this could be plus or minus, but we take the positive, of that because because x has to go from 0 to 1. Okay, so x has to go from 0 to 1. So we take the positive result. Oops.
So if we were going negatively, like if it was -1 to 0, then would you take the negative result?
Yeah, it's just, if it would have to be a different, it would have to be a different function. Let me show you what I mean. If we had y equals x cubed, right? Then we could do it, because y equals x cubed kind of looks like this serpentine type of thing, right? And then we could have something occurring over here. Okay, for y equals x squared, you're not going to get any intersection in this third quadrant. Does that make sense?
Oh, okay. Okay, yeah. I understand it now. Thank you.
So in this case, everything's positive where they intersect. So in order to keep things positive, we have to restrict, what our value is. Otherwise, if we took the negative, it would be over here. Right? That's where x's are negative. Okay, if we took the negative value here, it would correspond to this part of the graph, that part of the parabola. But because there's no intersection over there, and we're not talking about that, we only want to take the positive. Right? Okay. However, the radius, if I were to rotate about the y-axis, the radius of x equals y, okay, again, this guy is x equals y, and this guy here is x equals square root of y. Okay, the radius there would only be y units long. But what do I need to do? I need to increase this by how much?
1.
Yeah, 1 unit. So we need to increase that by 1 unit. Okay, so this is going to become 1 plus y as my radius. It's 1 plus y. That's my inner radius. So my inner radius is 1 plus y. If we were to only be rotating about the y-axis for the outer radius, the outer radius would go up to what? The
1
outer,
plus the square root of y.
yeah, it would go, if we're rotating about the y-axis, it would go up to the square root of y, but now we're increasing that to 1 plus the square root of y. The outer radius. So we're creating a washer, we're just increasing the length of the radius. Right? And we need outer radius minus inner radius, or basically outer volume minus inner volume. Right? Outer volume minus inner volume. Okay. So this is going to be the integral from what? What are we integrating from?
0 to 1.
0 to 1. Okay, that's going to create what we're integrating. Okay, I'll put the pi on the outside. We want the outer volume, which it means that we're going to take the outer radius and square it, right? So the outer radius here is 1 plus the square root of y squared minus the inner radius squared. That's 1 plus y squared. And this is with respect to what? dy. Okay, so now let's do some algebra. We have pi times the integral from 0 to 1 of 1 plus 2 radical y plus the square root of y squared, okay, minus 1 plus 2y plus y squared dy, 0 to 1. This is 1 plus 2 radical y plus y minus 1 minus 2y minus y squared. Okay. Okay, the ones are going to cancel. I'm left with pi times 0 to 1 of 2 radical y. This y here and this y here will combine to a negative y. And then I get minus y squared dy. I get pi times 0 to 1. I'm going to rewrite this as 2y to the 1/2 so I can integrate. Minus y squared dy. This is pi. Now we're going to integrate. This is going to become 2. Y to the 1/2 goes to what?
3/2.
3/2. Thank you, Daniel. So it's y to the 3/2. Then what am I going to put in front of that?
2/3.
2/3. Thank you, Corey. It's 2/3. Okay, this is going to become minus y squared over 2 minus y cubed over 3. And that is all evaluated from 0 to 1. Okay, so you've got pi times 4/3 times 1 to the 3/2 minus 1 squared over 2 minus 1 cubed over 3 minus 4/3 times 0 to the 3/2 minus 0 squared over 2 minus 0 cubed over 3. We're going to go pi times, this, all the ones just go to 1, all the zeros go to 0. So that goes away. We're left with 4/3 minus 1/2 minus 1/3. Well, 4/3 minus 1/3 is just 1. So that's 1 minus 1/2, which is just 1/2. So this becomes pi times 1/2, which is pi over 2. Nice. And that is section 2.2.